Hello students, this class is about the number of atoms in a unit cell. As you know, any crystal lattice is made up of very large number of unit cells, and every lattice point is occupied by one constituent particle, and this constituent particle could be atom, molecule or ion. Let us now work out what portion of each particle belongs to a particular unit cell. We shall consider three types of cubic unit cells, and for simplicity assume that the constituent particle is an atom. Now this represents the centrally located atom in the lattice. One unit cell is having this atom within it, so that means this is contributing to its maximum, that is 1. So a particle at the body center of a unit cell belongs only to the particular unit cell. It belongs to this, so its contribution is 1. Okay, now this is next case in which one atom is located between these two unit cells. This means that this atom is contributing to both of these unit cells, so its contribution will be 1 by 2. So a particle or an atom at the center of the face of a unit cell is shared by two unit cells in the lattice and contributes only 1 by 2 to a particular unit cell. So this representation shows that if particle is present between two cells, then it contributes 1 by 2. This should be kept in your mind, and let's see what is next. Now in this case we have to find the contribution of this atom which is located at the corner of this unit cell, that how many unit cells are connected around it and how much this is contributing in each unit cell. It has to be calculated, or that means we have to take an idea by simply having look at the drawing which will be representing that case. So this atom at corner is going to be connected to other unit cells which are surrounding it, and let's see how much it is contributing 1 by 1. Let's start numbering them 1 and 2. Here comes the 3 and 4. 5 and 6. 7 and 8. Now we have formed all possible unit cells around this atom. We now come to know that it is surrounded by 8 number of unit cells. That means it is contributing 1 by 8 to each and every cell that is surrounding it. So its contribution is 1 by 8. So we have seen that if the location of the unit cell is given, and we can trace out the contribution of atom when it is present inside the unit cell, or it's being shared with other unit cell. So this is the overall table formed in which we have location of the atom in the unit cell and its contribution to the unit cell. If the atom is body centered, in that case it will be contributing maximum to it, that is 1, and if it is face centered, So in that case it is contributing how much? Half, because it is in this situation surrounded by 2 unit cells. And then in case of atom at corner, it is contributing to 1/8. So let's proceed with another structures in which this will be very helpful to calculate the total number of contribution, the total contribution of atoms within those unit cells. For example, we'll be dealing with primitive cubic unit cell, body centered cubic cell, and face centered cubic unit cell. So let's start. So students, this is simple cubic unit cell, and it has atoms at its corners. We have just calculated, counted the number of contribution by each atom at the corner into a unit cell. So now let's calculate for this structure. This structure has how many atoms? 8 atoms, and each atom is contributing 1/8. So this value comes out to be how much? 1. Now by cancelling this value we are getting 1. So in this structure the contribution is 1 atom. So this is in case of primitive cubic unit cell, or maybe simply we can call simple cubic unit cell. This is body centered cubic unit cell. A body centered cubic unit cell has an atom at each of its corner. That means it has 8 atoms at the corners and also 1 atom at its body center. So let's see how much they are contributing. We have already seen through this table that body centered atom in a unit cell is contributing 1, and at the corners we have already seen it is contributing 1/8. So let's start. Let's see. So this one is contributing how much? 1, and these 8 atoms, again it will be written like this: 1/8 into 8, it comes to be 1, and when this 1 plus 1 is calculated or total, it will come to be 2. So 2 is the number. 2 is the total number of atoms per unit cells in body centered cubic unit cell. Now in case of face centered cubic unit cell, let's see. A face centered cubic unit cell contains atoms at all the corners. These are 8 atoms at the corners, and at the center of each face of the cube. So it has how many faces? 6 faces, and each face has 1 atom, and these atoms are shared with one more unit cell. Its surrounding, whatever unit cell present, it will be sharing this atom with it. This will be shared by the unit cell above it and beside this. So this is how they are being shared by the adjacent unit cell. So they will be contributing how much? They will be contributing 1/2, and these will be contributing 1/8. Now let's calculate how much their contribution is. How many? These atoms will be red colored. They are showing face centered position. So they are 6 in number. So ये हो जाएगा, this will be 1/2 into 6. It is 3. So let's see about the corner. It is again 1/8 into 8. It comes out to be 1. So total number of atoms per unit cells comes out to be 3 plus 1 equal to 4. This is the number we are looking for. So these are the contributions. So we have seen primitive cubic unit cell was contributed by 1 atom. In body centered cubic unit cells, 2 atoms were contributing, and in case of face centered cubic unit cell, we are having 4 atoms, though those atoms are contributing to it. Now let's see close packed structures. In solids, the constituent particles are close packed, leaving the minimum vacant space. Let us consider the constituent particles as identical hard spheres and build up the three-dimensional structure. So they could be used to build those structures in three different ways. So let's start with, we have these two-dimensional structures. Instead of three, I am using two-dimensional. These discs are representing atoms. And now this is close packing in one dimension. So there is only one way of arranging spheres in one dimension close packed structure, that is to arrange them in row and touching each other. This is how they are placed in one dimension. They are touching each other and forming a single line. In this arrangement, each sphere is in contact with two of its neighbors, like this. This one is in contact with the other two. Thus, the number of nearest neighbors of a particle is called its coordination number. In this case, one-dimensional close-packed arrangement, the coordination number is 2, because this atom is joined with two, is in contact with two other neighbors, so its coordination number is 2. So 2 is for this atom also, and this goes on. Now this is close packing in two dimensions. Two-dimensional close-packed structures can be generated by stacking the rows of close-packed spheres. This can be done in two different ways. This is the first way. They are placed just above the other. Let's see this. The second row may be placed in contact with the first one, such that the spheres of the second row are exactly above those of the first row. So in this case, they are just placed above. See what type of void or gap is forming. The spheres of the two rows are aligned horizontally as well as vertically. If we call this first row as A type row, the second row being exactly the same as the first one. So this is going to represent the same thing. What is going to happen? Similarly, we may place more rows to obtain a type of arrangement as shown in this figure. We have different layers and they are touching each other. Now let's see what is the coordination number. In this arrangement, each sphere is in contact with 4 of its neighbors. So that red colored line is also drawn. Thus the two-dimensional coordination number is 4. Also, if the centers of these 4 immediate neighboring spheres are joined, a square is formed. Hence this packing is called square close packing in two dimensions. So we have joined it. This line is starting from the center of this sphere and is touching the center of this sphere, and then we have used this line. Actually, we have connected these 4 spheres together by these lines, and this shows the coordination number for this sphere which is at the center. So this is how it is working. Now let's arrange some other way these spheres so that they are now touching to some other extent to each other. So we have two different types of arrangements for close packing in two dimensions. In the previous one, we just placed them like this, touching one another and having this type of gap or hole or void. Now in this case, we have just shift those spheres from this position. We have shift into this. Now the gap has changed. This is some different type of gap, though it is less in percentage as compared to what it was used to be when they were placed like this. It has larger gap, it is bigger void, and in this case they are more closely stacked together. So let's see what happens if this arrangement is followed and what is going to form. The second row may be placed above the first one in a staggered manner such that its spheres fit in the depressions of the first row. If the arrangement of spheres in the first row is called A type, the one in the second row is different and may be called B type. When the third row is placed adjacent to the second in staggered manner, its spheres are aligned with those of the first layer. So that means these two layers, this green one and this white layer of atoms, they are same. They are just positioned to a very similar type. Though I was not been able to arrange these discs at that manner, but still you can consider it to be positioned one above the other. And that means if this is A layer, this is B, then again it is A layer. So it comes out to be like this. The spheres of similarly placed fourth row will be aligned with those of the second row. So this row is same to this one, and B row is also similar to this is again, they are one by one again following the same, they will be forming the same structure. Hence this arrangement is of ABAB type. In this arrangement there is less free space and this packing is more efficient than the square close packing. Each sphere is in contact with 6 of its neighbors. So this is the one we are talking about. Now it has 6 neighbors, 1 2 3 4 5 6. So its coordination number will be 6, and the two-dimensional coordination number is 6. The centers of these 6 spheres are at the corners of a regular hexagon. Hexagon is forming. So this is two-dimensional hexagonal close packing. The triangular voids are of two different types. In one row, the apex of the triangles are pointing upwards, and in the next layer, downwards. So we are looking at these voids, triangular voids. In this case, the corner is upside, and this is down, upside down. This is just opposite to the other one, and this is how they are arranged in this particular arrangement. Now let's see close packing in 3 dimensions. Actually, all real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers one above the other. In the last section, we discussed close packing in 2 dimensions, which can be of 2 types: square close packed and hexagonal close packed. Now let us see what types of 3-dimensional close packing can be obtained from these. So we have arranged this layer. 3-dimensional close packing forms 2-dimensional square close packed layers. While placing the second square layer, close packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer. Now in the previous section we have seen that we placed one layer on the other, and now we have placed different layers together, and look at the void it is forming. That means they are just touching each other, and if a cube is formed, this is formed when the centers of these spheres are connected to each other. So in this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically, as shown in this figure. Similarly, we may place more layers one above the other. If the arrangement of spheres in the first layer is called A type, all the layers have the same arrangement. Thus, this lattice has A type pattern. The lattice thus generated is the simple cubic lattice, and its unit cell is primitive cubic unit cell. This is how we have already seen this is primitive because it has only 4 spheres, actually these 4 above and 4 below, which are connected together. Nothing body centered or face centered like condition. Now what type of 3-dimensional structure will form when these type of layers are placed or stacked one above the other? So in that case, let's see what is going to form. The thing which should be considered, uh, taken care of, is these voids, these triangular voids. Let's take it into consideration during our observation while placing these layers one above the another. In one arrangement of different layers, next layer could be positioned in a manner that the next layer, sphere of the next layer, is positioned just above the void. The gap it was already having is covered by this layer, and in that case next will be placed like this. So next layer will be covering those gaps, and this is the one arrangement. Other one is, this is one another arrangement in which the next layer is positioned so that it covers the gap when they are in contact. Wherever they are in contact, next sphere is positioned above. This is how they are covering the gaps. Now these two arrangements will result in different types of holes. Tetrahedral hole will be formed when the next layer is positioned just above the void or the hole. In this case, this is the lower layer and this is the upper layer. The atom covering this area will be positioned above it, and if the centers of these spheres are joined together with the center of the sphere positioned above, they will be forming a tetrahedron. So this is tetrahedron formed, and this situation will occur when the layers, different layers, are arranged in a manner that on the lower layer, when the atoms are in contact with each other, the other layer will be having atoms above those contacts. So this structure forms, and in that case, if the centers of all these spheres are joined together, you know, this is like for the lower layer, and this is for the ab or above layer having above arrangement, and this is what formed by them a octahedron. After connecting all these points, this octahedral hole has been converted into octahedron. This is the arrangement when the position is changed to the other point. So this is how the layers are positioned one above the another, and the voids which are being formed over there are shown by T or O. T for tetrahedral void and O for octahedral voids. These are formed when different layers are placed in this manner. Now let's locate tetrahedral and octahedral voids. We know that close packed structures have both tetrahedral and octahedral voids. Let us take CCP structure and locate these voids in it. So first let's begin with locating tetrahedral voids. We have this structural arrangement. Now we'll first place atoms at the required positions. Each small cube has atoms at alternate corners. In all, such small cube has 4 atoms. When joined to each other, they make a regular tetrahedron. Thus, there is one tetrahedral void in each small cube and 8 tetrahedral voids in total. Each of the 8 small cubes have one void in one unit cell of CCP structure. We know that CCP structure has 4 atoms per unit cell. Thus, the number of tetrahedral voids is twice the number of atoms. Now let's locate octahedral voids. Let us again consider a unit cell of CCP or FCC lattice. The body center of the cube C is not occupied, but it is surrounded by 6 atoms in face centers. Now this shows the atoms arranged at each face centered location. So we have 6 atoms. Now let's connect them. Thus, this unit cell has one octahedral void at the body center of the cube. Besides the body center, there is one octahedral void at the center of each of the 12 edges. It is surrounded by 6 atoms, 4 belonging to the same unit cell, 2 on the corners and 2 on the face center, and 2 belonging to 2 adjacent unit cells. So we have 2 on the corners, 2 on the faces, and these 2 belonging to the adjacent cubes. Now let's connect them to form the void. Here, only 1/4 of each octahedral void belongs to the particular unit cell. In a CCP, we have octahedral void, how many? 1, and we have 12 octahedral voids located at each edge and shared between 4 unit cells. So in that case, we have octahedral voids at edges, is equal to how much? 12 into 1 by 4 becomes 3, and we have total number of octahedral voids equal to 3 plus 1 equal to 4. We know that in CCP structure,
packing, HCP. Let us place third layer over the second layer. Here 2 types of arrangements are possible. 1. Placing the third layer of spheres on the tetrahedral voids of the second layer. In this type of arrangement, the third layer spheres are exactly the same as the first layer spheres. So the type of arrangement is AB-AB type, and the structure is called hexagonal close packing HCP. In this type, each sphere is in contact with 12 other spheres. 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. The total volume occupied by the sphere is 74%. Example, Be beryllium, Mg magnesium, Cd cadmium, Co cobalt, Zn zinc, Ti titanium, Tl tellurium, etc. Cubic close packing CCP of face-centered cubic FCC structure. 2. Placing the third layer of spheres on the octahedral voids of the second layer. In this type of arrangement, the third layer is not the repetition of the first layer. So this type of arrangement is called ABC type of arrangement. In this type, each sphere is surrounded by 12 spheres. 6 from the same layer, 3 from the top layer, and 3 from the bottom layer. So the coordination number is 12. The total volume occupied by the spheres is 74%. Example, Al, aluminium, Cu, copper, Au, gold, Pb, lead, Pd, palladium, Ni, nickel, and Ca, calcium. Body-centered cubic lattice. This arrangement is obtained when the spheres in the first layer are slightly opened up. That is, none of the sphere touches other in the same layer. Now, place second layer of spheres on the holes of the first layer. Third layer is repetition of the first layer. So this type of arrangement is AB type. In this type, each sphere is in contact with 8 other spheres, 4 from the top layer and 4 from the bottom layer. So the coordination number is 8. The total volume occupied by the spheres is 68%. Example, Na, sodium, K, potassium, Rb, rubidium, Cr, chromium, Mo, molybdenum, W, tungsten, etc. Calculating number of tetrahedral voids. In CCP or FCC, the unit cell is divided into 8 small cubes. Each cube has 4 atoms which are arranged in a tetrahedron. So 1 tetrahedral void in each cube and 8 in total. But we know that there are 4 atoms per unit cell. Therefore, the number of tetrahedral voids is twice the number of atom in CCP or FCC structure. Radius ratio of tetrahedral void, R void by R sphere, is equal to 0.225. Calculating number of octahedral voids. In CCP or FCC, the body centered is surrounded by 6 atoms which are present on face centers which generate an octahedral void. Along with 1 at the body center, there are 12 octahedral voids at the 12 edge centers, but only 1/4 of it belongs to 1 unit cell. Therefore, the number of octahedral holes is 4, 1 body center and 3 edge centers. 12 into 1 by 4 is equal to 3. So the number of octahedral voids is equal to number of atoms in FCC or CCP structure. Radius of octahedral void, R void by R sphere, is equal to 0.414.